Hi everyone. Today I will talk about our new work on Task-Agnostic Continual RL. So first of all, what is this setting? Well, Task-Agnostic Continual RL is a POMDP special case in which the hidden state of the world follows a non-stationary data distribution. And we often refer to this hidden state as a task. Okay, so because we are relaxing the assumption that this task distribution is stationary, this setting is much more practical, but also quite challenging, especially because of catastrophic forgetting issues. In our paper, we contrast task-agnostic continual RL with more popular reinforcement learning setting for better comprehension. Okay, so in any POMDP, one needs to handle partial observability to take optimal actions. This can be done by conditioning your agent on its full history, but that doesn't scale very well. A simple approach that scales better is to learn a working memory. So essentially, you can use maybe an RNN or a transformer to summarize the history of the agent into a context. This would be Z in our case. And this way, the agent can take optimal actions in a much more scalable way. So in task-agnostic continual RL, we often compare our agents to one of their soft upper bound, which would be the task-aware upper bound. So these baselines basically are operating in a fully observable world. In this way, we can understand how much is lost from having to handle partial observability. So this leads us to a first observation, which is that task-agnostic approaches will be performing fast adaptation on their context. Conversely, task-aware approaches will be trying to memorize all the tasks. We can refer to this as task memorization. This leads us to a first hypothesis, which is that depending on the setting difficulty, it might be more challenging to perform task memorization compared to fast adaptation. Okay? This would mean that task-aware approaches are not always an upper bound to task-agnostic ones. So to investigate this hypothesis, we created a synthetic toy experiment in which we could easily change the data and compute that is allowed, but also the dimensionality of the problem and the number of tasks. And aligned with the hypothesis, what we can see is, especially when the dimensionality of the problem is high, the RNN in black and the transformer in pink are much better than their task-aware counterparts. We took our baseline to a more realistic setting, which is robotic simulation experiments. And again, we can see that in the settings that we've studied, the RNN is able to outperform its task-aware and other task-agnostic baseline. So this is great. It also led us to a second hypothesis, which is that maybe the effect of hypothesis one are amplified in continual learning compared to multitask learning, because performing continual task memorization might cause a lot more forgetting than performing continual fast adaptation. So again, we investigated our hypothesis in the synthetic benchmark. So in blue, we have our best performing task-aware baseline. In the dotted lines are the multitask learning result, whereas the full line is the continual learning result. And aligned with previous literature, the multitask learning approach is an upper bound. But surprisingly, the task-agnostic approach is much better than its multitask counterpart, which is one, surprising, and two, great news for continual reinforcement learning. We further investigated why this hypothesis, first of all, we tested again this hypothesis on more realistic data, and we found that the RNN was able to match its multitask counterpart. So why might this be happening? Well, we investigated and we found some evidence that basically the RNN is able to reduce gradient conflict, which is inversely correlated with performance. So essentially, the RNN is the best approach at disambiguating the different tasks, which increases its learning efficiency and training stability. Thanks for listening, and please check out the paper.